Let's start with the isoparametric elements. Now we have last time seen the formulation for element stiffness matrix of 1D element based on isoparametric formulation. Let's consider once again, I will repeat the two nodate bar element. Let's consider two nodate bar element. Say node 1, node 2. Say let's consider this origin. This is Cartesian coordinate and natural coordinate. So the Cartesian coordinate, say L by 2, 0. Say consider the element of length L. So minus L by 2, 0 and plus L by 2, 0. Similarly, the natural coordinates, we know the natural coordinates, their values vary from minus 1 to plus 1. Let's consider this is minus 1, 0 and this is 1, 0. And also we know the relation between, for 1D element, natural and Cartesian coordinate is xi equal to x divided by L by 2. It's x divided by L by 2. Now, whenever we want to formulate the element stiffness matrix, we have to start with the displacement function. So let's assume the displacement function at any point within the element in terms of, say, functions. That is, say u is equal to n1 u1 plus n2 u2. Then let's find out the safe functions by using Lagrangian interpolation formula. So n1 is equal to, we know it's xi minus xi2 divided by xi1 minus xi2. So this is equal to, so xi is, the coordinate xi2 is minus 1 divided by, so xi1 is minus 1 minus 1. So this gives us 1 minus xi upon 2. Then the safe function at node 2, n2 is given by, so this is xi minus xi2 divided by xi1 xi2 minus, xi1 minus xi2. So this is equal to, so this is xi minus xi1 divided by xi2 minus xi1. So this gives us xi minus xi1 is minus minus plus divided by xi2 is 1, again minus minus plus 1. So this gives us 1 plus xi by 2. So what we get, the safe function at any point within element is 1 minus xi upon 2 u1 plus 1 plus xi upon 2 u2. Now the next step is to find out the strain displacement matrix, and see, in order to calculate the strains we have to find out dabba u by dabba x, but dabba u by dabba x is not possible because the expression in u is in terms of xi. So dabba u by dabba x is not possible. So therefore what we have to do, we have to express the geometric function in terms of same safe function. Then such an element in which the same safe functions are used to describe a displacement function and geometric function, then the element is said to be isoparametric element. So here dabba u by dabba x is not possible. So dabba u by dabba x is not possible. Hence, we have to describe geometric function. We have to describe geometric function by using same shape functions. Same shape functions. Thus, if same shape functions are used to describe both displacement and geometric functions, then the element is said to be isoparametric element. Isoparametric element. So if we use the same shape functions to describe both displacement and geometric function, then the element is said to be isoparametric element. So what is the geometric function? X equal to n1 x1 plus n2 x2. So this is a displacement function, and this is a geometric function. So n1 and 2 used in both the functions are same. If we use the same shape functions to describe the displacement function and this geometric function, then the element is said to be isoparametric element. Now here, differentiating both sides, we calculate dx. Now let's substitute n1 and n2. X is equal to 1 minus xi by 2 x1 plus 1 plus xi upon 2 x2. Now differentiating, dx is equal to, this is minus x1 by 2 dxi plus x2 by 2 dxi. So differentiating both sides. Let's take dxi common. So this becomes minus x1 by 2 plus x2 by 2 dxi. So now substitute for coordinates x1 and x2. So dx is equal to, x1 is L by 2. So this is minus L by 2 upon 2 plus L by 2 upon 2 dz. So now this becomes L by 2 dz. So this is J dz. So what is J? Now here J is called Jacobian constant, where J is equal to Jacobian constant. If it is 2D or 3D elements, then you will get J as a Jacobian matrix. Now, say from this, we can write down dx upon dz upon dx is equal to 1 upon j, and this is equal to 2 upon L. Now, so in order to derive the element stiffness matrix, the next step, second step, is stress. We have to find out strain displacement relationship. Or simply we write down the stress, development of stress. So it's a 1D element, epsilon x dabba u by dabba x. Now we can write down this as dabba u by dabba xi and dabba xi by dabba x. So dabba u by dabba xi and dabba xi by dabba x. Now this is possible. So dabba u by dabba xi, so this we can differentiate. Dabba u by dabba xi will be just a minute. Now we have, what is u? U is, this is 1 minus xi upon 2 u1 plus 1 plus xi upon 2 u2. Now dabba u by dabba xi is possible here. So this is minus u1 by 2 plus u2 by 2 so, and into, this is multiplied by d xi by, so this term d xi by dx, so this is 2 upon l. This is 2 upon l. Now we can cancel this. Now next, so let's simplify this. Epsilon x is equal to, so this we can write down as minus 1 upon L u1 plus 1 upon L u2. Now this is a strain displacement relation. In matrix form we can write down, this is strain 1 upon minus 1 upon L, 1 upon L, and this displacement vector u1 and u2. So in symbolic form, so we have this as stress equal to matrix B into delta. What is B? B is a strain displacement matrix, where B is called strain displacement matrix. Minus 1 by L and 1 by L. So once we know the matrix, strain displacement matrix, then the element stiffness matrix K, that we know K is equal to, so this is integration, triple integration, so minus B by 2 to B by 2, minus D by 2 to D by 2, and this is minus L by 2 to L by 2, into this is B transpose into D into B into dx dy dz. So this formula for element stiffness matrix we have derived by using the principle of minimum potential energy, that is the total strain energy stored or virtual work done must be equal to the total strain energy stored due to the stresses and strains. Now, so this is in Cartesian coordinate system. Now, say here also we know that, so this we can transfer into the natural coordinate system. So here we know that, but this matrix D is nothing but modulus of elasticity E for 1D, and integration minus B by 2 to B by 2 minus D by 2 to D by 2 dy dz is nothing but area. So this now K becomes, this is EA, we can take outside, minus L by 2 L by 2, it is B transpose into B into dx. So now the expression for K, element stiffness matrix K, is this. So next, so let's convert this into, this is still in Cartesian. This is still in Cartesian coordinates. So now in natural coordinate system, K is equal to EA. So this is -1 to +1. Then B transpose into B into d xi into J, that is Jacobian constant, and this is in natural coordinate system. Now we can easily now find out the element stiffness matrix for 1D element in explicit form. So next, so this K is now K is equal to EA integration -1 to +1 B transpose, matrix B is here, so the transpose of B, so we can write down this way, -1 upon L, 1 upon L, and this is -1 by L, 1 by L dx into J is 2 by L. J is 2 by L. So this is equal to, say let's have, we can take this, sorry, this is L by 2. J is L by 2. So this is, we can take outside EA L upon 2, integration -1 to +1, and this product, this is 1 upon L square, -1 upon L square, -1 upon L square, and 1 upon L square dx. Again, we can take L square outside and then integrate. So this becomes EA by 2 only, EA by 2L. This is EA by 2L. So only 1 L gets cancelled, and integration. So this is x minus x minus x x, so -1 to +1. So this now upper limit minus lower limit, EA upon 2L. So this is 2 minus 2 minus 2 and 2. So this 2 gets cancelled. So EA by L, 1 minus 1 minus 1, 1. So this is the element stiffness matrix for bar element, 2-noded bar element with axial deformation as a degree of freedom, which we have already derived in Cartesian coordinate systems, also by using the various approaches. Even we have used the energy approach, we have used the stiffness approach, and now this is by using variational approach, introducing isoparametric concept. So this is the element stiffness matrix for a bar element. So what is important, what is required is development of shape functions. So once you learn or you are able to develop the shape functions, then it is very easy to find out the element stiffness matrix by using the isoparametric concept. Now next, let's consider 3-noded element. 3-noded element. So in 3-noded element, again let's consider only U as axial deformation or degree of freedom.